Hey Chloe, glad you could join me for this episode. Today, we're diving into a fascinating paper about a new kind of accelerometer that uses a contactless suspension with a zero spring constant.
Hi Liam, yeah, this one caught my eye. Accelerometers are everywhere these days, right? In our phones, cars, drones. But I guess most people don't realize how tricky it is to make them really accurate.
Exactly. At the heart of an accelerometer is this tiny thing called a proof mass, basically a small weight that moves when the device accelerates. Traditionally, it's suspended by springs or beams that physically touch the frame.
Right, and that contact causes friction and mechanical noise, which limits how sensitive the sensor can be. It's like trying to feel a gentle breeze while someone's shaking your arm.
That's a great analogy. So the paper proposes suspending the proof mass without any physical contact at all, using a combination of magnetic and electrical forces to levitate it inside the device.
So it's basically floating? Like a tiny balloon inside the accelerometer?
Yeah, that's the idea. They call it a contactless suspension. And here's the kicker. They want to reduce the spring constant to zero.
The spring constant? That's like the stiffness of a spring, right? Like how tight a trampoline is when you jump on it.
Exactly. Normally, the spring constant pulls the proof mass back to its original position when it moves. But if you can reduce that stiffness to zero, the proof mass moves more freely in response to acceleration.
So the sensor becomes way more sensitive because the mass isn't being pulled back by a stiff spring. That sounds like it could detect even the tiniest movements.
Yes, theoretically, as the spring constant approaches zero, the sensitivity shoots up, even to infinity in the ideal case.
Wow, infinite sensitivity sounds amazing, but also a bit scary. Wouldn't the proof mass just drift away if there's nothing pulling it back?
That's a good point. The system needs to be carefully controlled using closed-loop feedback. Basically, sensors detect the mass's position and apply forces to keep it stable.
So it's like having an invisible hand gently nudging the mass back into place whenever it moves too far.
Exactly. This approach also reduces mechanical thermal noise, those random vibrations caused by physical contact, which improves accuracy and extends the sensor's lifetime.
That's a big deal. Less noise means better readings, and longer life means more reliable devices.
Now about the physical setup. The proof mass is a small disc made of conducting material. Underneath it, there's a coil carrying an alternating current, which creates a magnetic field.
And then there are 4 electrodes arranged around the proof mass, creating an electric field?
Right. The coil induces currents in the proof mass, generating magnetic forces that levitate it. The electrodes apply electrostatic forces, which can be adjusted by changing the voltage.
So by combining these magnetic and electric forces, they can fine-tune how stiff or soft the suspension feels.
Exactly. The paper goes deep into the math, using Lagrange-Maxwell equations to model the mechanical, electrical, and electromagnetic interactions.
I'm not going to pretend I followed all the equations, but it's clear they developed a solid model to predict how the proof mass behaves and under what conditions the spring constant can be minimized or eliminated.
Yes, and importantly, the model shows it's possible, in principle, to achieve stable levitation with zero spring constant.
Stable levitation means the proof mass stays suspended at a fixed height without drifting or falling, right?
Exactly. And the model reveals some interesting design constraints. For example, the radius of the coil and the radius of the proof mass must not be equal.
That's intriguing. So the size difference between the coil and the proof mass actually helps keep the mass stable?
Yes, and the levitation height is limited by the difference between those radii. It's a neat insight that guides how to build the device.
Now, about compensating the spring constant. The inductive suspension creates a positive spring constant, pulling the mass back, while the electrical suspension creates a negative spring constant, pushing it away.
Exactly. By carefully adjusting the voltage on the electrodes, these two effects can cancel each other out.
And the paper shows that applying a very small voltage, about 196 millivolts, can reduce the spring constant to zero.
Yeah, that's surprisingly low, less than 1/4 of a volt to achieve this delicate balance.
That makes the approach practical, not just theoretical.
Definitely. And with the spring constant eliminated, the static sensitivity of the accelerometer increases dramatically, by an order of magnitude or more.
Plus, the steady-state error in closed-loop operation decreases significantly, meaning the sensor stays accurate over time.
And since there's no physical contact, mechanical thermal noise is reduced, improving the sensor's lifetime and long-term stability.
This could really push the boundaries for inertial sensors used in aerospace, military, and even consumer electronics.
Absolutely. It's also worth noting the collaboration behind this work. Researchers from Singapore's Nanyang Technological University and Moscow Aviation Institute in Russia.
It's great to see international teams working together on such cutting-edge tech.
So to wrap up, this paper proposes a novel way to build ultra-sensitive accelerometers by levitating the proof mass without contact and eliminating the spring constant.
The combination of inductive and electrical forces backed by solid mathematical modeling shows this is feasible.
And the tiny voltage needed to achieve zero spring constant is a practical advantage.
Overall, this innovation could lead to more precise and reliable sensors in the future.
Yeah, it's exciting to see how fundamental physics and clever engineering come together to improve everyday technology.
Definitely. Well, thanks for diving into this with me, Liam.
My pleasure, Chloe. Looking forward to our next deep dive.